So in this demonstration, we will study the Rutherford scattering of alpha particles. Our aim is you have to study how the scattering rate varies with respect to scattering angle, and also will determine the atomic number of the target material. So this is our experimental setup. This experiment clearly demonstrates the existence of a small positively charged atomic nucleus as proposed by the Rutherford. Let us first understand the experimental setup. The experimental setup consists of an americium-241 alpha source. So this is the alpha source we are using over here, and which is actualized in the source holder. Then we are using the thin gold foil, and also we are using the aluminum foil. These are the two different foils are used here, aluminum foil, and this is our gold foil, and we are using a slit aperture. We have two different type of slit we are using. This one is 5 mm width, and this one is 1 mm width you are using. So this aperture we are placing here. Let's say actually we are 5 mm gold foil we are using. It will be placed here. We are placing at the holder. It will be tight. Yeah. So once we tight, then we can place over here, and there is a detector, which is a silicon semiconductor detector. Okay. So now we are placing the source and this thin gold foil slit aperture in the chamber. Now you can see that the alpha particles emitted from the americium-241 source pass through this is actually 5 mm wide slit and strike the gold foil and are scattered at different angles. So these scattered alpha particles are detected using this silicon semiconductor detector. Now actually we have to vacuum it. For vacuum we are using a vacuum pump. So we have to turn on the pump. Here it is. Once you turn on, so you wait for some time. So the chamber will be vacuumed. Once vacuum, then we have to start the experiment. So during the measurement, the pump may run continuously, or the chamber valve may be closed after the evacuation. So this is the discriminator preamplifier. So the detector is connected to the discriminator preamplifier using a short 25 cm cable to minimize the noise. Connect the scattering chamber and the discriminator preamplifier and the counter exactly as shown in the diagram, the circuit diagram. Now switch on the counter. Once you switch on the counter, select the gate time. For that actually you can see that to operate the counter there are two modes. One is the mode is there and the gate is there. So first we have to set a time, how much time we have to use. So for that, let's say to select the gate time for 100 seconds, suitable for actually this is suitable for small scattering angles, and for large angles or weak signal longer gate time up to 1000 seconds may be used. The counter is normally starts correctly in pulse counting mode with this NAE activated and the gate time set to manual for more than 100 seconds. So you can, if you use the time more than 100 seconds, you press the mode and gate simultaneously. Simultaneously press. Then if you can increase the so you can see it is increasing. For a higher value you press the mode, and for lower value you press the gate, so it will decrease the timing. So whatever the desired value you want to set, you just release and it will show over here that this time you have to measure. That means this is set to at 400 seconds. Now before starting the experiment, first we have to set the discriminator level. So for that, we first so before starting the experiment, first we have to set the discriminator level. So now in the scattering chamber, you rotate the swivel arm to a large scattering angle, let's say actually 30 degree. So you keep it at 30 degree. At this angle, very few alpha particles reach to the detector. Then we have to set the time for 10 seconds by press the gate. Then turn on the potentiometer fully counterclockwise, setting the discriminator level to 0. At this setting, no discrimination occurs. Every noise pulse passes through. As a result, the counter will be overloaded immediately. You can see in the display. Now slowly increase the discriminator level by about a quarter turn and reset the counter. By careful turning the potentiometer up and down, find the point where the noise count rate just drops to 0. So now you note this position carefully. Next, what to do? Next, rotate the swivel arm to 0 degree. So before it was 30 degree. So now you place the 0 degree where the alpha beams points directly at the detector. Now large number of alpha particles will be detected at the detector. You can see over here. The counter will slow. The counter will show some counts. So slowly increase the discriminator level again until the count rate just begins to drop and begins to drop. And note this second position as well. Now set the potentiometer exactly midway between these two positions. The position where noise is completely suppressed and the position where true alpha count start to drop. So once the discriminator level is set, so we will start to measure the scattering rate versus the scattering angles. So before start the experiment, you cover the scattering chamber with this black cotton so that outside lights will not fall over here. Now actually you record the scattering rate versus as a function of the angle. So as per this table, okay, so you can vary measure are taken symmetrically, let's say at different angles from starting from 5 degree to 10 degree, 15 degree and 20 degree. You can actually symmetrical measurements help identify any miselement in the setup. At each angle, we count. You can count the in a particular timing. You set the timing as per we shown before, and measurements are repeated several times, and it should be average. Then you measure the pulse count and you take the mean value, then counting rate you calculate as per the table. Then from this data you plot the scattering angle versus f of theta. The measured counting rate decreases rapidly with angle, confirming the inverse square angular dependence predicted by the Rutherford formula. So to determine the nuclear charge number, we replace the 5 mm slit with a 1 mm slit to improve the angular precision. First, measurements are taken with gold foil at plus minus 15 degree for 100 seconds. Then the gold foil is replaced by the aluminum foil. Because aluminum scatters few particles, so we increase the counting time to 1000 seconds. Now comparing the counting rate for gold and aluminum allows us to calculate the atomic number of aluminum. So in conclusion, this experiment beautifully confirms Rutherford's nuclear model and the role of atomic number in scattering strength. Thank you.